Well, good afternoon, Max. Good to see you again.
Yeah, thanks for having me.
Yeah, this would be, I think it's our second or third training session that you and I have tag teamed to take on some interesting topics.
Yeah, I like this format. It's fun to kind of do a back and forth like we're sitting in the office like old times. So
Well, we have a really good turnout for today. So for those that don't know who you are, Max, why don't you just take a minute and tell everybody who you are and what you do?
sure. My name is Max Rohr, and I'm one of the education and training managers at Caleffi. I started my career helping my dad tie pipe to the ground and doing radiant systems back in the early 90s, and then have worked at the manufacturer, wholesale, and rep level before coming back to Caleffi about 9 months ago. So
Awesome. Well, and I'm Michael. I am the technical services manager at Eden Energy Equipment. Eden Energy Equipment has been around since 1981. I've been with Eden now for just over 20 years, and now I've got gray in my beard, Max. I remember when I started, I was a little thinner and I didn't have gray in my beard. So Eden's a quite unique company. We have a full technical design team. So we have 2 engineers on staff. We have technical people that will help with startups and commissionings, or just simple things like answering questions on systems. We firmly believe in having true partnerships, whether that's with Caleffi or IBC or the good folks at TACO. There's a variety of companies we deal with, and we're very selective in who we deal with because we want to make sure that all of our projects are obviously a success. So as far as what we're going to be discussing today, Max and I are going to be talking about electronic and thermostatic mixing considerations. It's worth noting that this course, or this 1-hour training session, was by request. We didn't dream this up. We can thank some customers who reached out and said, hey, can you guys do a presentation on thermostatic mixing considerations? So we're going to talk about electronic and regular thermostatic mixing valves. We're going to talk about how to size them. Max and I are going to talk a little bit about some piping options. We're going to talk about the always dreaded recirculation creep and what that means and what that can do. We're going to talk about thermal disinfection, and Max is going to show you some pretty cool pre-assembled options you can look at. And then lastly, we're going to talk a little bit on balancing and a general overview of how that works. Now, as far as takeaway handouts goes, we have one handout that's available for download for everybody who's in attendance. So this is issue 22 of the Caleffi Hydronics books. As far as reading material goes, I can't think of anything better than hydronics, other than maybe Siggy's book. So it's a really good collection of books. The link to get it is on the top of this slide. You can also register there so that you'll get notification of the electronic version. And if you're like me and you like to sit on the couch sometimes and read the hard copy version, you can also get a hard copy mailed to your shop. So right off the bat, one of the things that Max and I want to talk about is the whole conversation of thermostatic or electronic. And really, whether you go thermostatic or electronic, you have to ask yourself a couple of questions. And the first question you got to ask yourself is, do you actually need automated thermal disinfection? So depending on where you're located, I'm in Ontario, obviously, and Max, tell everybody where you are right now, I guess.
yeah, Salt Lake City.
Yeah, so the rules are going to be a little bit different depending on where Max is versus where I am, but obviously thermal disinfection is very important, and in some scenarios, especially if it's a school or a hospital, it becomes much more important. But at all times, you want to keep it, front of mind that thermal disinfection is very important. The other thing in deciding whether you're doing thermostatic or electronic is pretty rudimentary. Do you have electricity available? Can you actually go in and put in an electronic device, and is that a viable option? There are some projects where you simply can't do that for a variety of different reasons. The other thing to keep in mind is, did the last valve scale itself to death? Did you have a water quality issue? I was out with a really good plumber this morning who was telling me about a job where they've replaced the mixing valve more than once. And again, that's something to keep in mind, not just whether I'm doing thermostatic or electronic. And while that electronic one that Max is trying to sell is more money than the thermostatic, again, if you've got scale issues, keep that in mind. It could be more money up front, but long-term savings on the project. The other thing we got to keep in mind, and we're going to talk about this, is that whole high and low flow situation. We have to make sure that whatever we're doing, that we're not just designed for peak flow. And we have to ask the question, are we replacing a high-low mixing station? Is there a scenario where we might need 30 to 35 gallons a minute at full flow, but on minimum flow, we might only need 2 gallons a minute? We have to think about that. There's a bunch of ways to do that, which Max and I are going to talk about. We want to make sure we can achieve that. And then the last thing we're going to talk about is what is the pipe sizing being used? Now, you always want to pay attention to your pipe sizing, as we all know. You want to be conscious of your flow velocities, and we're going to talk about that. And at the end of the day, we want to make sure that system's going to work properly. It may seem simple to say, hey, let's make sure the pipe size is right. Like, who would ever make the pipe size wrong? But having reviewed the list of people who are here for the training today, I know that Tom Gervais can point to many jobs. Welcome, Tom. Good to have you. And I know Patrick Scantlebury can point to many jobs where, okay, yeah, we intended for them to do it in 4-inch copper, but they decided to do it in 2. And what does that mean to the design and the issues that come with the system? So the project example number 1 we're going to talk about is sort of the non-engineered project. This is the one where there's no drawings to be found. You have no idea what your minimum flow is. You have no idea what your maximum flow is. So there's really limited data. And you've all seen this. So this is a real job. So you get sent a photo. In my position, you get sent a photo. We got this boiler in a room, and then there's another room next to it, and that room's got some water heaters in it. So this particular job, I had the opportunity to go to site before it got done, and I got to go to site after it was done and it was commissioned. So we definitely want to pay attention to what we have and try to achieve a solution that makes sense. One of the things we'll see a lot is that people will look at a job and go, well, I know how big the boiler needs to be. This old boiler is 500,000 BTU, so clearly that's what I need. And then you'll notice, okay, well, I think they had about 12 water heaters. We'll just base it off 12 water heaters. The reality is that's a pretty expensive solution. And Max is going to walk you guys through, some sizing guidelines and rules you can use, because there's an awful lot of systems that are designed and sized, and we're using the word design loosely, where somebody licked their thumb and went, I think it's this, right? That's not what we're trying to achieve here. The reality is we'd rather spend a little bit more money up front, or maybe in some cases less money up front, and just do the math to make sure that the situation is going to turn out properly. So this job in particular, once everything was right sized and selected, this is what it looked like when it was installed. So this ended up being 2 SL boilers by IBC. So one's a 399, one's a 115, right size, so we get a really deep, good modulation on it. And in this case, it's tied to a Thermomax. So the sizing with this was done using the IAPMO calculator, which Max is going to talk a little bit about here in a minute. So it's a nice condensing, well-designed system. The Thermomax is a really cool product just because it's a reverse indirect. We're not actually storing potable hot water. I'm sure many of you are familiar with that. But really, the big thing was that we freed up an awful lot of real estate. And I never thought about this when we designed this. That big old room that had a gazillion water heaters stored inside of it, well, it turned into a profit center for the landlord. Like, the landlord liked the new heating and domestic system, but what they really liked was that they could put washers and dryers in and actually turn that into something where they could make some money off of it. So at that point, Max, why don't you just really quickly talk about some of the sizing considerations we have to look at and where this all starts?
So I think in the 2 slides ago, they started with a bunch of different sizes of cinder blocks, and they said, okay, what water heaters can we put on top of these so they'll all line up at the top there? So I guess if you want to, turn back the clocks, Winston Churchill was just became Prime Minister of Great Britain. That's when these Hunter's curves calculations started. So a lot of what we do in plumbing is still rooted in these Hunter's curves calculations that were done 80 years ago. And what we're finding, the deeper that we look, is that they are oversized for what we're doing with modern plumbing, as kind of a general statement. It's going to depend on the type of use case and things like that. But as an example, if you were going to do something that was a 10-plex of just regular sized condos or something like that, using these calculations, you might come up with a design peak flow of 50 GPM. And then with the more modern calculators, like we'll show on the next slide, it might be 19. So it's really taking a deeper look at which calculator you're using too, because you might end up with a much better system, smaller pipe sizes, smaller components, less expensive, and more importantly, better performance instead of having something that's maybe 2 times oversized for what the actual use case is, incorporating some modern feedback like the IAPMO group is doing with their calculator. So something that they're actually talking about, it's a little hard to see on that slide, but November 4th, if you're interested, they're doing a water demand calculator summit where you can remote in to this virtual conference. I think it's a day long, and see kind of how they're adjusting the calculations for 2021 use of these of these plumbing components. So currently they have a water demand calculator version 2.1. You can go in and type in all your fixtures, select if it's a single family residence or multi-unit, and it's going to spit out a number that will surprise you if you're used to using the Hunter's curve, because it's going to be a lot smaller. But what they're finding is that it doesn't mean that it's any noticeable difference in the performance. May even be better as far as hot water wait times and things like that. So something to take a look at, whoever's helping design your plumbing system. This is some kind of a modern take on the Hunter's curve that's really important.
Yeah, I think the other thing too is like this is a really good tool. So if you guys actually go to iapmo.org, just the link we have there, you can download this as an Excel spreadsheet, and you can use it to do your calculations. I think it's one of the better ones out there. Various manufacturers have very good tools as well. So a shout out to Lars. Lars has the right spec. It's just larsrightspec.com. Anybody who needs that, email me afterwards. I'll be happy to send you that actual link. So you can go there. You can use that for sizing domestic or sizing boilers. And even companies like Thermal 2000 out of Quebec or Bach, they all have these guides that you can use for sizing the domestic hot water. And I don't know about you, Max, but me personally, I will dabble with different ones. I don't always use the IAPMO calculator. I don't always use the Lars Right spec, but I would say those two are my favorites.
No, and manufacturer specific is helpful too, because you're probably going to get a model number or a couple different choices instead of having to transpose all this information and then line that up with some other chart somewhere and figure out what the appropriate piece is. So if you know the manufacturer that you want to use and they've got a nice calculator like you guys are using with the Lars stuff, that's a great way to go too, because it's going to help simplify the rest of the process as far as sizing and pricing the job.
100%.
All right, so one of the first of many things to look at with a mixing valve is, what is your minimum flow requirement? So let's say you installed that big Legio mix on the right, the flanged 3-inch mixing valve, and you installed it in your house, and then you go down to the sink and you're trying to just have a trickle of warm water to shave. You are going to be so far below the minimum there that it's not going to perform properly. And the reason is the water kind of sneaks past the sensor in the center of that valve that's used to modulate the valve. It's not enough to wash over the entire chamber basically and give you a good accurate reading. So it can hunt a little bit at those really low flow rates. So going back to the far left there, the sink mixer, that's a point of use mixing valve that's meant to go under a sink, and it goes all the way down to 0.35 GPM. So that's going to be the appropriate valve for just a single shave situation, or a normal up to 2.3 GPM under a sink. That's the valve that you want for that particular use case. If you're looking at a hospital or a city block, then maybe you go with the big 3-inch flange Legio mix on the right there. But one of the things that you should look for with the mixing valve is what is published in the technical brochure for minimum flow rate, to make sure that you're in the ballpark there. And then you kind of go up in size across from left to right. So in the middle there, that Thermostatic 5231 mix cal, the minimum flow rate is as low as 4.4. And then the difference with the Legio mix is it actually can go really low because it's a single ball valve that can close really tight. So one of the big differences in thermostatic and electronic with a ball actuating the flow with the Legio mix is that it can close completely the hot, and it can open just a crack, where with thermostatic mixing valves, they have a cartridge that's going to slide up and down, and you might have 90% hot and 10% cold, or vice versa, but they don't generally, except for a couple exceptions, close one or the other hot or cold completely. They're not really meant to do that. but a valve like the Legiomix can do that, and it's the reason you can get to a smaller minimum flow rate too. So those are a couple little things. One big note here is that if you're looking at a commercial job and you're selecting an 1.25" valve or something like that, the recirculation pump does count towards that minimum flow rate. So if you think, well, for an 1.25" valve, 4.4 is a little bit higher than that single unit turning on a shower or something like that, you're counting the recirc pump as part of that to get to that number. So that should be more achievable if it looks like 1.25", 4.4 is too small for your minimum.
Yeah, there's sort of, it comes back to that discussion, Max, of you'll look at it and you'll see, oh, well, it's an 1.25" line, so I'm going to put an 1.25" Legio mix in this, or a 1.25" mix gal in it. We have this conversation over and over again. We don't care what size connections are there, what size piping is there. We care about what the min max and the design flows are that we're trying to achieve.
Yeah.
You can very easily oversize a mixing valve for the application, which we see quite a bit.
Yeah, and of the questions you posed at the beginning, what is the existing pipe size is potentially the most misleading, where some of the other factors are more important. And the biggest one is knowing what your max flow rate is and using a calculator if it's an existing building to figure it out, because it could be a 3-inch pipe and you need a 1.25" valve for the actual load because it was oversized. So yeah, that's a good point.
Yeah, so as far as how to come up with those solutions, why don't you just quickly sort of talk about the different minimum flow solutions that are out there?
So in the past and currently with thermostatic, if you don't have an electronic option, you don't want to go to an electronic mixing valve, you don't need any of the other features there. What you can do is, this is a station that you can buy from Caleffi, a single part number that has a small mixing valve on the bottom. And then as soon as that can't keep up, you start to see some fall off pressure with the PRV in the center there. And then the big mixing valve starts to open. So it's two different valves. The picture on the right was one that was field installed before we had PRVs in the North American market, so that you can see behind the pipe there's a small mixing valve and then a bigger mixing valve in the front, and they have two stations. So in that case, you may have struggled to find a single mixing valve to cover all of those different things. So maybe you're going down to that 2 GPM, but you might need to go up to 50, 60. It can be hard to do that with a single thermostatic, which is why high-low stations are popular and have been a good way to go for a long time. But there are different ways to do that, and they can be also a little tricky to set too. There's no specific number on that PRV that you're going to set that's going to work for all job sites. There is some commissioning involved with that to make sure that the bigger valve is coming on at the right time.
Yeah, so it's a very viable solution, but the reality is that whether you're the engineer designing it or the contractor installing it, this wouldn't be my first choice today. There's other things available, and we're going to talk about one of them that, you're going to have a small price premium associated with it, but unless you enjoy being in high-rise buildings at awful hours of the early morning, balancing this and setting it up, there would be other things that you'd probably want to look at, which we'll talk about those considerations as we go on. So the other thing that's really important it gets overlooked, it doesn't matter whether it's a mixing valve or whether it's just simply a zone valve, is the CV. So Max, walk us through the whole CV and how that's important here.
Okay, so let's say that you size the job and it's 1-inch pipe. It's the only thing you need a 1-inch mixing valve. Which 1-inch mixing valve do you need? So in the Caleffi catalog, we've got the MixCal, and then we've got the MixCal Plus, which is a much bigger valve body. But look at the different CVs. So the valve on the left is a 3 CV, and then the valve on the right is up to a 7. So same 1-inch connections, but completely different size bodies there. So to go back a little bit, CV is a measure of efficiency at allowing fluid flow. So the example on the left to find CV, we've got a delta P of 1 PSI, 60-degree water, with 3 GPM. So that matches what that 521 on the left is there at 3 CV. It's going to lose 1 PSI as you flow 3 GPM across. So CV of 3. So go to the middle one. So we can plug in those other numbers. All 3 of these are related. So if we say, okay, we can measure that there is a 20 PSI drop across that valve. It's a CV of 3 valve. We know that from the literature. So the calculated flow of 13 GPM has a pretty big penalty there in PSI. So usually no more than 5 or 10 is what engineers will look for in a mixing valve. So we can do it, but we're taking a pretty big pressure penalty to get up to that 13.42 GPM. So now let's say we switch to the bigger valve, the graphic on the bottom right there. So it has a CV of 7. Our max flow that we need is 13.42 GPM. It only has a 3.68 PSI drop. So that is a much better valve for that use case there. It's more expensive because it's a lot more brass, but you're not going to take a 20 PSI penalty. You're only going to take a 3.5 PSI penalty. And it's not something occupants would notice, where if you went with the smaller valve with 1-inch connections, you might have some lazy faucets that you're not getting the pressure that you thought, or other devices might not work well in a plumbing system if you're losing 20 PSI still in the mechanical room. So those are a couple things that we look at when we size a valve, is that maximum flow number that we need. If it is 13.42, we can kind of easily rule out that smaller valve. It's not going to be able to keep up without losing too much pressure.
Yeah, I think, again, this is another one of those takeaways that just understand, just because you've used a 1-inch valve in the past doesn't mean that this other branded 1-inch valve is going to operate the same. If you've ever been inadvertently burned by a CV number, which I know I certainly got very close to being burned by a CV number with a Caleffi product, where I made a selection. Unfortunately, we did actually check it and go, ooh, Cody and I on the team were looking at that going, this is the wrong valve. So you always want to pay attention to that. It's important that you keep an eye on it for sure. So
yeah.
Input and output temperatures. Let's talk a little bit about this, Max, from the standpoint of our domestic hot water source.
Okay, so as Cody Mack, Caleffi, one of the other trainers, says, the mixing valve does not add heat to the system. So if you set your water heater here for, let's say you need 120 out, you cannot set that water heater for 120 set point. It will not be able to mix with anything and maintain 120 out. So in this case, you would need to add 18 degrees to that, and that's going to be your set point for the water heater. So mixing valves are going to publish that minimum temperature difference between hot and mixed outlet. It applies more to thermostatics, and I'll talk about that a little bit later, than the Legio mix, which is an electronic ball. But you can't have a mixed set point of 120 and have the same set point at your water heater. You're going to lose those 18 degrees, and you're going to have taps that are colder than you had expected, because you are mixing some of that cold water, and that's why you need to set it hotter. But the good news is, and I think that you've had a lot of experience with this too, Michael, is that you can make that water heater seem like a bigger water heater if you store it warmer too. So that can be helpful in the selection of these components too.
Yeah, I think that's one of the things that gets overlooked quite a bit. Is you look at that and go, I'm putting this device in as an anti-scald, as a protection device. Well, the reality is, yeah, we want to make sure we don't have any issues with health and safety, but the mixing valve is going to boost that output. I think the other thing that is important to note, what Max said, is that in the case of this particular valve, it's looking for 18 degrees difference. It's not every valve. Not every valve is the same. Just as we're about to talk about the Legio mix, and Patrick has a question on the minimum on the Legio, which we'll talk about, it's not the same as using this product. So it's a little bit different. We're going to talk, so another example project, and again, this is a real world project, and again, this one is an engineered design, so it's a little bit different. We know what our minimum flow is. It's going to be about 2 gallons a minute. We know that our maximum flow is going to be 30 gallons a minute. And it's a spa and resort facility. So it's really important that we tick all the boxes from the standpoint of, obviously, health and safety always. We want to make sure we've got the capabilities of doing disinfection. And we want to make sure that under no scenario does Max or Mike or the contractor get a phone call of, we don't have anywhere near enough hot water for this spa when it's at full capacity. So in this particular plan, we are going to be using NUPI PPR plastic pipe. And it will be EX boilers. So it's, there's a lot of design considerations that go into that as well. So looking at this, we've talked about it, and why don't we just sort of walk through really quickly how that selection would look, Max?
Sure. So let's say we want to try a thermostatic just as a first pass at this. So mixing valves are going to have these flow curves in the technical data. This is the best way on the bottom right there to actually see what the different flows look like for the CV of the valve, because it is, you know, a curve like that. You can look at the chart in the middle there and get a general idea that, okay, 1 inch minimum of 4.4 GPM, maximum of 40. That is closer, but we want to look at the chart and see what the actual delta P is for those conditions. So if we said that the flow conditions here are 2 to 30, you can kind of see where I put on the lines there in the green. So it looks like this is going to be a good fit for 1.25 inches, if you kind of can see in more detail there. Oh, sorry. Back one more. So 1.25 inches is where, if you pull up the chart, it lines up, because we want to stay out of that red shaded area at the top, which is where we get past 10 psi of pressure drop there. So that 1 inch model isn't going to keep up there. We bumped up to the 1.25 inches, and that's closer because we've got the ability to do that 2 to 30 range. So 1.25 inches there. So let's try it on the next slide with the Legio mix. All right, so I've got the similar chart. We've got the red shaded area at the top with that 10 psi drop. So the crazy thing is with this one is, with the flow conditions that we have, that 2 to 30, you could go all the way down to a 3/4 inch Legio mix. And part of the reason is they're inside of the chamber. The CV of these valves is a lot better because it's like a wide open ball that's modulating, instead of kind of a tight passage through a cartridge that slides up and down. We've got great CVs through these valves, and it's a reason that if you started with the 1.5 inch trunk piping and selected an 1.5 inch Legio mix, you're going to be way oversized. And we've got another sizing way to show that on upcoming slides. That's a simplified version of this. But if you really want to get into the weeds and make sure that you're doing the calculations properly, I'll walk through the chart on this slide here. So the easiest way to do it is to look at the recommended flow rates, and we'll say, okay, minimum is 2.2 GPM for that 3/4 inch valve on the top here. And then design flow of 27 is perfect. We were looking for 30 there. You could even go more wide open and hit 43 with the maximum there, because that CV is 9.7 for a 3/4 inch valve. So that's pretty huge compared to the thermostatic that we looked at even at a 1 inch side a minute ago was 3. So that's part of the reason that we can go down to a smaller size with the Legio mix. If we want to take a deeper look, so this next chart down here takes a minute to walk through, so I kind of highlighted the different steps. So first, we're going to look for in the yellow shaded area, the minimum GPM 2.2 is great. We were looking for a 2 GPM, and if we've got the recirc hooked up to this too, we're going to be plenty over there. Design of 27, so all that looks good. Now we go to the green shaded area. So we want to see what the pressure drop is across that valve. A lot of engineers shoot for that 7.5. Some will go up to 10, some will go down to 5, but we recommend that 7.5. So if we look at the green shaded area there, now I can walk down below that 27. That's our design GPM. Below that, let's say we were using all 3/4 inch pipe. That velocity, the red numbers are going to be in feet per second. That's pretty high. So 16 at 3/4, one down is 10 at 1 inch pipe. And then we're starting to get a little bit more reasonable with 1.25 inch pipe at 7 feet per second. In this case, everything's going to be sized well if we do a 3/4 inch Legio mix, but going all the way over to the blue on the very right, we still want to keep that 1.25 inch trunk piping. So it's going to look a little weird on the wall, but at 1.5 inch piping, we're at 5 feet per second at 29 GPM, and then the Legio mix at the 3/4 inch is going to be the right valve in that application. So you could go to a 1 inch, and you would be close enough in this case, but it is something that is going to look a little strange, but is going to be sized properly as you walk through this chart to leave that 1.5 inch trunk that connects all the way down to the 3/4 inch Legio mix. you want to do that as close to the legio mix as possible. You don't want to take 50 feet of that building and cut it down to 3/4, but you're just going to go right down to that. That CV is so high, it can take those higher flow rates and move through it well. So one of the other things to mention with the legio mix is it does have 100% hot water close off, which is important and will come up in the piping a little bit later too. So that's part of the reason that we can get to those really low flow rates and still be able to close off properly. Is it's not a cartridge that's always got 5 or 10% of hot and cold open. It can shut it down all the way, and the minimum flow rates to have it open full hot, we don't have to have that same 18-degree temperature difference that we do with the cartridge style thermostatic. So that's one of the questions that Michael brought up earlier too. We can open all the way hot or all the way cold. We don't have to have that same, we don't even publish it because it's not really the same animal for the minimum difference between the storage temperature and the outlet temperature, the mix temperature.
Yeah, I think the big takeaway from the slide that we've put together here is right off the bat on the far right-hand side where you see it, the 10 feet per second. My personal take is just pretend that doesn't exist. Don't use that. You're begging for trouble on that. You have to be conscious of that 5 feet per second. That really is the magic number you want to pay attention to. But again, it comes down to what material are you using. Max might be using copper. I might be using Nupi PBR. It's going to come into play on it. The big takeaway is it's come up 3 times now, I think, is that just again, because you've got 1.25 inch or 1.5 inch piping going into the building, does not mean that legio mix or whatever mixing device you're using is going to be the same size. If you do take it down, whether it's 3/4 or 1 inch, I think you could argue for either in this scenario. Just understand that does not mean that you've got 30 feet of 1 inch or 3/4 inch pipe coming off of it. You're going to have all kinds of problems with that, and I would be terrified of seeing what the pressure drop and velocity would be going through the piping on that. A few comments with people who did the math in the background. That's how you can always tell when you've got smart people participating. And they've rightly pointed out that at 30 gallons per minute, thank you, Patrick, be careful what pipe size you're using because your flow velocities are going to be very high.
And like you pointed out, that 5 feet per second, outside of that, the copper development handbook isn't going to like that for copper. And then for PEX as well, you're going to go slower through that. And that comes up a little bit in the balancing too. But you do not want to be sending hot chlorinated water through any piping material at 10 feet per second all the time. Your recirc pump is going to be oversized if that's the case. You risk pinhole leaks through the copper. It's just not friendly to plumbing systems to be going that fast with hot water through a house or a commercial building.
Yeah, I think everybody just looks to it and goes, oh, well, the pipe's going to fail. And then you have guys go, well, I know I've never seen pipe fail. It's that erosion of the pipe and what else it's going to damage in the system. The pipe is not a huge concern. I know in Toronto, there was a run of bad pipe that came back to a manufacturer offshore, right? But at the end of the day, it has to be properly sized because the biggest thing is you will get a phone call of this is not working properly. We're having issues. We're not getting hot water. And you likely will have component failures. I don't know how at the flow velocities that Max is talking about, saying don't do this, at those flow velocities, you're definitely going to have some sort of issues. Whether it shows up now is to be seen. And the other thing too, always to keep in mind is just because you didn't see it on the job doesn't mean that the guy that replaced you and took over that work didn't fix it for you. I think Max and I have both been there. We just don't know it yet. Not everything I did was perfect. Max and I like to share stories about, wow, I remember when I thought this was the right way to do it. Just because we don't get asked to fix it doesn't mean somebody else is not fixing it for us. The other thing we want to have a conversation about is recirc creep. So recirc creep has some symptoms. Obviously, the number one thing we're trying to prevent is the gruesome burns that you can potentially get. Basically, what's happening when you have recirc creep is it's long periods of time where there is very little domestic hot water demand. And so what'll happen is the first person that gets up and cracks that tap, they're the ones that are getting that blast of hot water that can potentially result in scalding to whoever turned that tap on. So preventing recirc creep is very important. We want to make sure that we don't have this, because nobody wants that phone call where we've burned a small child, or we've burned whoever, whether we burn Max, we don't want to burn him either. It's very important we pay attention to this. So we've actually got a pretty good illustration. Max, walk us through the illustrations, just starting from the far left where we're stable.
So stable, let's say it's a hotel. That's just at noon or 4 p.m. or something like that. Occupancy is high. People are taking showers. They're, washing their hands. There's a load on the building for the hot water. So we're bringing in some cold water. We're mixing cold water with the hot water from the tank. The outlet's 115. So let's say it's starting to get later in the day. Maybe there aren't as many people that are using the fixtures. We're starting to lose some of that demand, and then creeping up on the third one, we are sending 125 out, but we're not really shedding any of that. And especially if it's a well-insulated line like it should be, we're not getting ice cold water coming back into the port. So we're not mixing that whatever it may have been 50-degree Fahrenheit water on the left anymore. We're starting to get 123 back or something like that, a warmer temperature. And then on the bottom right, what's happening is no one's using any fixtures. So we're recirculating up to 145, and then we're only losing a couple degrees through the piping, and that's what our cold is now. So our hot is 150 or 160 or something like that, and then we're getting 143 back in as the cold. And a thermostatic mixing valve can't keep up with that unless it can close 100% off the hot. Which some of the valves do, but most of them don't. So at that point, we have exceeded our set point because we don't have anything cold to mix the hot with, and that's when that first person getting up to turn on a fixture in the morning could get a blast of hot water, and then it goes away. So it's kind of a tricky symptom, because then as soon as somebody takes a shower and hopefully they don't get burnt, it's going to go back to that far left stable condition again. So it's a little hard to figure out, but the thermostatic valves cannot always close off that hot completely, and that's where you can start to creep. So you can pipe your way out of this with the next slide.
Yeah, I think the big thing here too is that you mentioned it, Max, from a diagnostic standpoint. So you, as the contractor that has the maintenance contract, if you haven't seen this before, you get the call of, okay, somebody burned themselves, and you go out there at 11 a.m. in the morning or 2 o'clock in the afternoon, and you can't reproduce it. Doesn't matter what suite you go into or where you are, you're not able to reproduce it, because it's only showing up when that one person just rolls the right dice that they're going to get that sort of blast. One of the questions that came up, Max, and it's a good one, is would a aquastat solve that
problem? It can. One of the weird things is that there are some places that, like OSHA is saying, do not use an aquastat, because then you're not recirculating warm enough water. So there are all these different kind of stakeholders that are weighing in on how to do this differently. And an aquastat would be helpful, because then your recirc gets up to that temperature and it will turn the pump off. But now you're stagnating all night until that temperature drops. So it can help in one spot and maybe create another issue in another spot. So the better way to do it is to pipe it differently to prevent that creep, with or without the aquastat, depending on what your local rules are. So this is a sheet that we send in the box with all the Legio mix valves. So the important thing, the difference is you have two different options with the Legio mix, because it can close the hot water 100%. So in that case, you're recirculating whatever your maximum mix temperature was. It's going to dissipate some heat in that recirc line, either quickly or slowly, depending on the insulation. But you're not mixing blazing hot with warming temperature all night. It will just close that hot completely, and you don't have it creep. So the first way that you can pipe it here is that, and you might have to help me out with the mouse on this one, is coming back to the Legio mix. In this case, we do not need to have any sort of, or in this case, we need to make sure that we're getting water back to the tank and then also to the cold inlet of the tank With the Legio mix, it's going to have the ability to close 100% on hot. So this piping is one of the options with the recirc connection. So if you were going to pipe in a thermostatic mixing valve, that last one would be the way that you would go. And if you are not, so I always get tangled up in these these diagrams. So in the case you're using a thermostatic, you have to have the ability to throttle like a globe valve down. So you're sending some of that tank, some of the recirc water back to the tank and not all of it right back into the inlet of the valve. It's a tricky commissioning step because you have to, in the middle of the night when there's no demand on the building, you have to have somebody go in and throttle that globe valve down. So you're sending, some of that back to the tank and not directly into the cold inlet. It's a very manual, it's a very kind of nuanced installation. So one of the things that Michael and I were talking about before is that the price of the Legio mix, even a smaller one, an electronic mixing valve, is going to be more expensive than a non-electronic thermostatic mixing valve. However, to install it to prevent the recirc creep piping, there are more steps involved there. And then you need to have the globe valves. Back one slide. You have to have the globe valves to balance that. So there's additional components in play here, and it's a little bit more work. So if you look at the full installed cost of the Legio mix versus the thermostatic, it can make more sense to just go with a valve that's going to protect from that recirc creep, regardless of how you pipe it with either of the two diagrams that we give you. You don't need the globe valves for balancing because it will close off that hot completely. So that's something to keep in mind for just the overall installed cost of that. And there is a much more concise version of what I just said that we did, that Cody Mack did at our shop, that's on our YouTube channel. That's ways to prevent recirc creep, that goes through that diagram a little bit better. He's been around that diagram longer than I have. But the takeaway is, because the Legio mix can close 100% the hot, you don't need to play games with how you balance the flow coming back from the recirc. You're going to be fine with either of these two piping arrangements and can save some commissioning money and startup money on the labor side.
Yeah, I think one of the challenges too is that when you look at a job, you have to look at the job with the labor limitations we have currently. The reality is that the Legio mix, even if it's a few $100s more, which I expect it would be, I'm expecting it's a few $100s more than the more traditional way that we would do it, the piping implications are much, much simpler. So somebody who has done this for a few decades looks at it and goes, this is easy for me to do. I can set this up. I don't mind going in at some unreasonable hour to get this all balanced and set up. The reality is that using modern technology is going to work a lot better and be way more cost effective, because you're not going back to redo it because you had somebody learning how to do it, or having to set it up that didn't quite have the same level of experience that some of the people who've done a lot of these would have. One of the other questions that comes up as well, Max, is with the recirc creep again. Would thermal traps help or hinder from the standpoint of recirc creep, or should we worry about it at all?
So it's a good piping technique to incorporate, but I would use one of these two piping diagrams that we send, regardless of the trap that you create with the piping. The best protection is just going to be to have the ability to close that hot 100%. Is probably the best way around all this. And something that should be mentioned is that these pointed distribution mixing valves, like the Legio mix and the MixCal Plus, the MixCal that are going to be in the mechanical room, are not scald protection devices. So these are meant to mix the temperature down to send out to the building. They are not the last line of defense. You want to use a point of use mixing valve to have the ultimate stop, basically, to make sure that the hot water doesn't hit a tap, and that's going to prevent the recirc, the creep issue as well. That's an important piece of it. So nursing homes and things like that, for sure. The Legio mix, as well as it will work to close off that hot water, isn't the ultimate. That's what point of use mixing valves right under the sink or right by the tub are built for. It's a different certification. So,
well, especially if we're using the disinfection cycle, which we're going to talk about as well, right? We
that's
want
a
to be
must.
very
Yeah,
conscious
that would be a must. Yeah. So to kind of recap here, These two Caleffi products, the Legio mix and then that angle mix that has the angle pattern that's nice to put right on top of a water heater, that will actually close 100% the hot as well. So that's a thermostatic that can close the hot completely. The rest of the line of thermostatics, at least from our catalog, you will need to pipe to prevent that recirc creep if you're using a recirc pump. So those two don't require that midnight, what is the temperature coming back with zero load commissioning step that you'd have to do with a globe valve.
Yeah, so and this one on the far right would be a very cost-effective solution. We're not going to be using that in the projects we discussed at the beginning of this. It's just simply not going to be anywhere near big enough.
No,
And the
that's
reality
more
is the Legio
residential.
mix would fit nicely into that budget. I don't want to put a $800 valve into my own house. But one of the other things that Max and I've talked about is we're all very guilty of this, where we design a system and we look at a valve and go, that's too elaborate, or it's too high tech, or it's more money than they want. The reality is that what I can afford or what Max can afford is completely different than what other people can afford. And again, when it comes to health and safety, we need to be paying attention to that and not cutting any corners on that front.
And there are a lot of different ways to do it. You might split up the system and have two 1-inch mix cals, and the CV lines up for you to just split the east and the west wing of the building, or it may line up that you do a 3/4 inch Legio mix. Completely different budgets, but kind of different animals as far as the mixing goes as well. So we'll get into thermal disinfection with this slide here.
Yeah, so thermal disinfection obviously is very important. Max and I have already touched on there's just certain applications where you don't want to be taking any chances. Schools and hospitals and things of that nature. We need to make sure that we do have a disinfection cycle. This again comes back to what Max said, is understand it's not going to be an anti-scald device. If we've got a disinfection cycle on this, and if it's in the process of running that cycle, we don't want somebody turning a tap on because they will end up with considerably hotter water, like 160 degrees coming out, and that's a bad news situation. So it does require an electronic mixing valve, and it does need to have a disinfection control logic built into it. It has to maintain that for a certain period of time. So typically it's 15 to 30 minutes, but again, it depends on what temperature you're at. As Tom Gervais liked to remind me, it's not a published number, but we all have those charts where we know how long does it take me to kill this. So if I've got the water at 140 degrees, then guess what? It's going to run for 30 plus minutes. If Max has the water set at 180 degrees, it's going to be way less than that. But again, we have to be conscious of the fact that we can't have people trying to draw water off a tap at that temperature. Obviously, it has to circulate through the entire system. It's the same discussion we have with indirect tanks, where we don't hold indirect tanks at 100 or 120 degrees because we don't want that bacteria to grow. So it has to circulate through the entire system. And again, to sort of beat on that issue, we have to make sure we have point of use or some other means of anti-scald to make sure we don't have any protection issues. Typically, thermal disinfection has a lower initial operating cost. Obviously, it's safe for people, which is great. There's no pollution, there's no flushing. Max and I, we were talking yesterday and kind of joking about the other ways that you can treat, whether it's the silver ions or chlorine or my personal favorite, pickling vinegar. At least the pickling vinegar, Max isn't going to die when he drinks that, but the thermal disinfection option really is the route that we want to go with this. So again, just sort of reiterating that point, we have a chart here where we're just sort of outlining again, where Max has got his at 180 degrees, his thermal disinfection time is going to be significantly less. Whereas in my scenario where I'm at 140, 32 minutes. So I was pretty close to what that number would be. So you obviously want to pay attention to that as you're sort of doing the system.
And one of the things that is important with that too is that, and this slide might even be a better way to describe it, is if you're going to do thermal disinfection, you need to verify that temperature all the way back at the end of the recirc loop. So you may be supplying 160 degrees at the outlet of the mixing valve, but if this is some huge school with uninsulated pipes in the basement or something like that, you may still be getting back 120 degree, and that's not going to cut it. So what you can do with the Legio mix is you can program what that return sensor is going to see and say, you need this to get up to 140 and you need to maintain that for 32 minutes. Then we're going to consider that disinfection cycle complete. You could up the supply temperature and reduce the amount of time that you need to see that. But instead of, you could try thermal disinfection with the thermostatic mixing valve, and what you would do is go down to the mechanical room, turn it up to 180 degrees. You know, you've got the point of use protection all the way around the building, and then put your hand on the return and wait until it comes back hot enough that you can't grab it. That's not scientific enough that we would trust that, or trust somebody to do that in order to disinfect the line. So we program that into the control and let it automate that at 3 in the morning on a Saturday. And every week you've got a data logged, verified thermal disinfection cycle that is, you know, a legal asset for you too, to say nothing left this mechanical room above this temperature, and also we disinfected at this date to this temperature. We verified that we've taken it out of the comfort zone for legionella, and this is all, you know, data logged for 30 days. That can be a very important thing to have on your side, to make sure that you can prove that you're doing your job well, and something that is generally very, very hard to say that, no, this valve did not scald anybody.
Yeah, so the big thing that's different is just this right here, right? This has got a brain to it. That's exactly what this is. So it has a display on it. It's, you know, it's not a laptop, you know, but you can go in, you can see your disinfection cycle. To Max's point, if somebody ever called and said, "Oh my goodness, this happened," you can actually go and you can look. The other nice thing, and we'll show it a bit later, is that this can be integrated into a building management system. So you can actually tie this into their automation system. They can log data, you know, as much as they like to see what's going on. And then obviously, again, to our point of this not being an anti-scald device, our drawing has the sink mixers in it to make sure that we're good. And obviously, the big draw of this control is that making sure that as the water goes through the system, we make sure we're actually coming back at a temperature to make sure, okay, the whole system is in fact part of that disinfection cycle. There's no chance we have anything in there.
So on the next slide, the difference here is we are now in disinfection mode. So let's say it's, you know, we're supplying 160 degrees now. So we're applying 160 degrees coming out of the mixing valve. Let's say there's a lot of heat loss and it's coming back at 140. We keep that for half an hour. We've disinfected, you know, the lines that were up to temperature there. However, water is lazy, so it's going to take that path of least resistance up that first riser. We haven't really guaranteed that we've sent that warm water all the way out to the riser on the right. So now what we need to do is balance that. So there are a lot of different balancing valves on the market, and this one just in the diagram is important to make sure, I'll cover it kind of at the end, that we're getting that proper temperature to all of those risers. So this valve, it has a knob on the top that you set to a temperature. So you could say, I want coming out of that riser, on the return from that riser, that needs to hit 130 degrees. Or in disinfection mode, we actually open a second orifice and it lets up to, you know, 160 or 140 through that cartridge to make sure that we're not just disinfecting the path of least resistance, but we're disinfecting all of the risers and making sure that the balancing valve is kind of playing traffic cop there to make sure that hot water goes where it's supposed to disinfect the largest volume of water and the biggest amount of branches as possible.
Yeah, and a new install where you have control over this piping that I'm highlighting, you know, you can make the argument that, okay, maybe I don't need to have this balancing, but the reality is this is a really good idea to have these thermal setters. There's a whole variety, and I think Max and I have something further in the slides that shows some different options. It definitely is a good idea, and the thermal setters, just being able to set that temperature, to me, that's kind of a no-brainer method of setting that up. Lots of questions coming in, lots of good questions. That's why I keep looking to the right. For everybody who wonders, why does Mike keep looking to his right? So Max, you talked a little bit about this. Talk a little bit more about the pre-assembled stations that we have here.
Yeah, so these are both single product part numbers from Caleffi that we can send, you know, mounted on the unistrut like that. So that would be the Legio mix in the center with the proper recirc piping with the check valves in the right places. That's just going to be, you could just press right onto that with your recirc line, select your recirc pump correctly, and you're good to go. One of the questions that we had before the class was about certain jurisdictions requiring a pre-assembled skid, so that would be a good way to go. And we also have that in the high-low mixing valve. We call that the Delta 2, that would have the piping correct for a small thermostatic and a big thermostatic with the PRV in the middle. You still have to set that in the field, the PRV, but it's going to be piped correctly. So those are nice selections for engineers too, if they just want to say, I want it to be exactly like this. And it may or may not be at the end of the day, but this gets you started with all the most important components in the right places.
Yeah, I can't say we've used any of these pre-assembled ones, but it does make a lot of sense. We're big fans of this new Legio mix. It's a good product. Again, I'm not sure I'm going to throw that in my house or your house. It's a little bit overkill.
No, that's a commercial product for sure.
The options are definitely there for us.
Yeah. Okay, so we've got a lot of different balancing valves on the market, some from Caleffi, some from other manufacturers. Manual, where you've got a Venturi and you're just adjusting that. You've got your charts out, you've got your upstream, downstream with the Venturi effect, and you're matching up whatever your desired flow rate is with the flow chart. So static, pressure dependent. Automatic would be something like the FlowCal, which is kind of the vertical blue valve in the center with the temperature gauge. So that is you're going to pick a cartridge with the GPM that you desire, and it's going to, within reason, there's a minimum and a maximum GPM, keep that flow rate where you want it, because there's a cartridge with a different flow pattern that's going to come in and out with the spring to make sure that you've got the 4.2 GPM, whatever you pick. That's a great way to go. People use those on a residential application on a recirc line with PEX or something like that to make sure you don't exceed that 2 feet per second. You just pick the cartridge and say, okay, this is the cartridge that I want, to make sure that we're not racing back through that recirc line. Would work for copper as well too. So I think the next click in this application for thermal disinfection, what we're talking about is this thermal valve thermal balancing valve, the thermosetter. So what this does is you have a temperature solution to a temperature problem. So if you say, in normal operation in this riser, I want to have 120 degrees all the way on the return, you set the knob on the top for that temperature, and it will modulate up and down to allow that temperature to come up and down, not to exceed the temperature that you set there. It doesn't ever close 100%, so you don't deadhead your pumps, but you are basically automatically keeping up with the demand of the building too. So not theoretically, we should have X number of GPM through that riser, but if your demand is low, you start to close off those risers until they need it. And that's important for energy savings as well. So the way this works with thermal disinfection is there's a second cartridge that can be opened with 24 volts, or there's an option to have a thermal cartridge that when it sees a certain temperature, it opens a bigger orifice basically and lets that hot water through the risers to complete the thermal disinfection, and then it falls back into normal operation. So kind of a multi-use valve. It's been so popular that we have a different version that's just the thermosetter without the disinfection mode, because it's just a nice way to balance risers or laterals to set a temperature and walk away from it and not have to get your charts out or have a balancing contractor even come to the job. Anybody can set the temperature.
Yeah, I think it's a cool feature of the model where you actually have that actuator where if you put 24 volts to it through the disinfection cycle. Now, will they be able to pick up that 24 volts off the Legio mix?
That would be through the building management system. So
Gotcha.
That would be something there are a couple different ways that you can program it, that you could use a relay and go through it. But the cases that we've had, there's a building management system that's going to open them and maybe even stagger them open depending on the complexity of the system.
Yeah, for sure. So if you're not doing a disinfection cycle, obviously the cartridge styles ones are really nice. Max and I've talked about it. My only concern with styles like this is noise. I've been to jobs where, depending on the building and the pressures, these can make a racket. These ones in the bottom right are a personal favorite of mine. I really like those. The only challenge with these, plug your ears, Max, is they're expensive.
Well, depends on how expensive your balancing contractor is, because that valve, again, you take a wrench and you adjust it, and then you pull that pin and you verify your flow rate, and you're done. where we have
Yeah.
a high-rise project in Florida, and he's like, I'm gonna get off of this job a month earlier because I don't have to send a balancing contractor to every single unit in this, this high-rise construction. So they're going to do the thermosetters, set the temperature, and then they go back down the elevator and they move on to the next job. So again, it comes back to the what's your labor worth part, that someone will beat you on price with a manual balancing valve, but they may not beat you on the overall cost of that job.
Yeah, I think it's worth like this one here, which is a good selection. The challenge is you're replacing a cartridge, whereas this one you've got the pull pin on it. You pull that pin, you dial your flow in, and if it turns out you're off, then you just adjust it. These, depending on which size you purchase, will dictate the flow capabilities of them. We use them for hydronic applications. We use them in heat pump applications for ground loop side. Like they definitely
PTO,
are
yeah,
good controls. But
yeah.
that's a great statement, Max, on the labor. It's the same thing I'm saying with the Legio mix. This is not inexpensive, but it's going to save you a pile of money when it comes to your balancing time for sure.
Yeah.
I think that the next one we're going to show is just going to talk a little bit about the building management system. So the Legio mix by itself doesn't need to have the Modbus interface. It does have a nice little display on it. We've done a few of them now. It's very easy to set up. You can then connect that to a building management system. It's not an inexpensive adder to it. So sometimes we'll get the feedback I just gave on the flow setters if they're a little bit pricey. The BMS interface on a Legio mix, you're probably looking at $1,500, give or take. But if you look at a building automation system for a high rise, $1,500 is nothing to them. The automation for that building is going to be six figures and not low six figures. It's very expensive to do. And if you're dealing with a hospital or a school or anything where you've got sensitive people in the building, again, this is an insurance policy. The protection from a liability standpoint is absolutely important. So.
Yeah, and Modbus and BACnet options, depending on what your language is. But then read write too. So then the automation company can decide to push all those different parameters into a disinfection mode. So that's really what we're talking about. You wouldn't want to do it for your house for sure.
Absolutely. So as far as sort of wrapping up the whole thing, we obviously want to make sure that you pick the product that makes the most sense for your application. Again, are you going to use the flow setter and save it on balancing, or are you going to use the cartridge style and you're not so worried about the balancing costs? Maybe you're not the guy doing the balancing or the gal doing the balancing, so you don't care. Look at the big picture. That building owner could really appreciate it if you save them a lot of money down the road. The other thing we always like to talk about is always try to cover yourself, future-proof your designs. Try to prevent any issues you're going to have. Patrick's made a really good comment in the questions box that liabilities can be very expensive, and certainly we want to be very conscious, especially when we're dealing with domestic water that people are drinking, that we protect people. Forget the liability aspect of it. I don't want to make anybody sick, much less have somebody die as a result of anything that I've done or Max has done or any of our customers have done. And I think it's one of those, it's a pay me now or pay me later. You can pay more money up front for the Legio Mix product, for example. The Mix Cal will work in a lot of places where the Legio Mix does, but if you've got water quality concerns, or if you need that disinfection cycle because of the application, or if you're just dealing with major scale issues and you're going in there every 4 or 5 years, are you saving much money by doing that? Probably not likely. As far as handouts goes, I think we already covered that. We have the handout that's available as a download. Hopefully you'll have some good takeaways from this. If you have questions, by all means, put them into the question box. I know we've got a pile that I'm going to go through here. And I think the big thing I want to articulate is don't be shy. If at the end of this webinar, you get up tomorrow morning and you have a question about something I said or Max said, you should all have my email address. If you don't, it's going to be on the screen in a second. By all means, ask questions. Max and I are definitely here to help you and answer any questions that you may have. Max, any final closing thoughts before we move on?
One of the things I don't think that I mentioned from a technical side is the scale. With the Legio Mix, what it does is it rotates the ball, the full stroke once a day. So that helps kind of scrub the scale off of that ball as it rotates the full stroke. A thermostatic mixing valve may scale because it isn't forced to go the full range ever. It just kind of slides up wherever the use is, and that can be a reason that they don't perform, is that they scale themselves into a too narrow band where the Legio mix opens and closes the full stroke all the time once a day to keep that scale from building up and limiting the operating range.
Yeah, no, I definitely agree. So let me just really quickly see if there's any questions that we didn't cover. Yeah, good question. Could we descale a thermostatic, or would it be just as good to replace it?
So I would say a lot of them are just replaced because people don't want to take the time to descale them. But you're going to want to use the Michael special with some pickling vinegar is a good start because you can drink it. You can get more aggressive with whatever chemicals that you want, but know that if you're going to descale that and put that back into service, somebody's going to drink out of that. So it's something to pay attention to. Some people, since they're all unions with all the products that we talked about, will have another valve body, put that in, descale the first one and rotate two. But I think it's like a lot of products. I think people are just getting, it scales, they get frustrated, they replace it. It scales, they get frustrated, they replace it, then they switch brands or something like that. If scale is a big concern in a commercial project, you might need to switch to an electronic to help out on that front. But yeah, definitely vinegar is a good place to start and see how much of the scale it gets out.
Yeah, you'll be pretty surprised. The story behind how I switched from chemical cleaners to vinegar was I bought the cheapest house on the nicest street, and it was a rental. There was university students living in it, so there was a water softener, but it never saw any kind of salt. So everything was a mess in that place. And the nice part about pickling vinegar is it's a little bit stronger than traditional vinegar. It's still dirt cheap. For $10, I bought enough to fix all my issues, whereas a $40 jug of cleaner wasn't working so great. I like the fact that it's safe to drink. You might wonder why you're drinking French fry juice, but that's certainly nice. It's safe with most materials. Like you're okay with PEX and copper and PPR as a general rule. Typically, I don't call it pickling vinegar. It sounds fancier if we call it acetic acid. So stick with that. You sound smarter than saying I'm going to Zehrs or the grocery store to get some vinegar to flush your system. So next question is there a minimum temperature differential for the thermal valves?
Yeah, so for the thermostatic valves, it's going to be that ballpark for the different line that we offer, 18 degrees or something like that. It may be a little bit bigger or smaller, but yeah, if you want optimal performance out of that valve, and whatever you're storing your tank, you need to incorporate that you're going to have a 18-degree difference with what your desired set point is, or you're going to have to bump up the temperature of your water heater.
Yeah, and obviously check the manual. We're assuming you're
Yeah.
using Caleffi products, but check the manual. Depending on whose product, it could be quite a bit more. There are valves out there, you got to add another 9 degrees to that number to get effective mixing on that valve. So you want to pay attention to that for sure. Good comment by Patrick. Patrick's just pointing out that for domestic hot potable water, people aren't supposed to be using that for direct consumption. I have 3 small children in my house that use it for direct consumption when I'm not looking. So we obviously want to be very conscious of that. I feel like we answered most of them at this point.
Yeah,
obviously, if there's any questions we didn't get to, you can obviously email us afterwards. We appreciate everybody that took the time to hang out for us with the last hour or so, and we look forward to having everybody in our next training session. So as far as what's upcoming and planned, Bob Rohr is going to join me probably next month, and we're going to just do some shop talk, I think, and maybe Max will join us for that as well. It'd be more interesting if we dragged my father into it too, because Max and I are quite similar that way. I learned all my good habits and my bad habits from the guy I apprenticed under, which is my father. He doesn't know how to do a webinar, so I don't think he'll ever join us, but we'll see, Max, if I can manage to pull that off. It'd be very entertaining.
That'd be good.
And then we're also planning to be doing our 3-part seminar series with John Siegenthaler, who's a friend of both Max and I. And lastly, we're going to be doing a live design session. So what we're going to do is we're going to design a system in CAD. We're going to sketch it all up. Max is going to join me for that. We're going to sketch a system up, and we're going to do it right, and then we're going to do it a little bit wrong, and we're going to talk about what's wrong about it. And, that'll be a very open discussion, and maybe we'll try to drag a third person into the discussion as well, so we can have a really good open discussion about it. So on that note, Max, as always, it's a pleasure seeing you, and I appreciate you joining us. And
yeah, thank you.
Thank you to everybody who hung out with us for the last hour.
Thanks, everyone.
All right. Thanks, guys. Take care, Max.
Thanks.